Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Have you ever noticed how some things in physics always seem to stay the same? Like we know a rolling skateboard eventually stops because of friction, but why does it have to stop at all?
Right.
It turns out there's this super elegant idea called Noether's Theorem that connects this everyday observation to why the laws of physics are consistent throughout the entire universe.
It's a really powerful concept. Noether's theorem helps explain why certain quantities in physics, things like energy momentum and angular momentum, are conserved. The fascinating part is that it ties these conserved quantities to fundamental symmetries in nature.
Okay, I'm intrigued, but I have to admit the word symmetry in physics always throws me off a bit. What does that actually mean?
Think of it like this. Imagine a perfectly round ball. If you rotate it, it still looks exactly the same.
Yeah.
Right? That's rotational symmetry. In physics, symmetry basically means the behavior of a system doesn't change, even if you make certain transformations to it. For instance, the laws of physics work the same, whether you're here on Earth or on a distant planet.
That's an example of space translation symmetry.
So is Noether's theorem saying that whenever we find this kind of symmetry in physics, it points to something being conserved?
Exactly. Each continuous symmetry has a corresponding conserved quantity. A classic example is time translation symmetry, the idea that the laws of physics are the same yesterday, today, and tomorrow. This symmetry is directly linked to the conservation of energy.
Wow, so the fact that physics itself is timeless leads to the conservation of energy. That's pretty profound.
It really highlights how deep these connections run. Noether's theorem reveals a fundamental link between these abstract ideas of symmetry and the concrete observable laws that govern the universe.
This is reminding me of those optical illusions where you see one image and then suddenly a whole other image pops out at you. You think you understand something, and then Noether's theorem comes along and shows you this whole other layer of meaning. So how about another example? I need to wrap my head around this. Let's go back to that frictionless pool table. If you hit a billiard ball, it will keep moving in a straight line forever. That's because of space translation symmetry. The table is the same everywhere, so there's no preferred location. This symmetry leads to the conservation of momentum, which basically describes the quantity of motion an object has.
So because the table's location doesn't matter, the ball's momentum has to remain constant. I think I'm starting to get it. What about rotational symmetry? I'm picturing a spinning figure skater.
Perfect example. As a figure skater pulls their arms in, they spin faster. That's a demonstration of the conservation of angular momentum, which is tied to rotational symmetry.
Okay, I can see how Noether's theorem isn't just some theoretical idea floating out there. It's deeply woven into how the universe actually works. It's like this hidden code that unlocks a deeper understanding of the laws of physics.
That's a great way to put it. And the amazing thing is that it doesn't just apply to the things we can see and experience directly. It's a foundational principle that extends from classical mechanics to quantum mechanics and even to Einstein's theory of relativity.
This is already blowing my mind. We've only just scratched the surface. To really grasp the power of Noether's theorem, I feel like we need to dig a little deeper into some of the underlying physics. Can we talk a bit more about the idea of action in physics?
Action is a really important concept in physics, but it can be a bit tricky to explain. It's a mathematical quantity that we calculate for a physical system, and it helps us understand the path the system is most likely to take. Imagine it's like nature's always trying to be efficient, finding the path of least resistance, so to speak.
So where does symmetry fit into all of this? I'm guessing it's not just about pretty patterns.
You're right, it's much deeper than that. Symmetry in physics means that even when you transform a system in a certain way, the action remains the same. It's like saying, no matter how you look at it, the fundamental principles stay constant.
Okay, can we walk through an example? I'm a very visual learner.
Let's stick with that pool table, but this time, let's imagine we shift the entire table 5 meters to the right. The physics of the game, how the billiard balls move and interact, wouldn't change at all. That's space translation symmetry in action. And it means that the action of the system remains constant.
And Noether's theorem connects this symmetry to the fact that momentum is conserved, right? That's fascinating. But how do we actually prove this connection between symmetries and these conserved quantities? Does it involve a lot of complex math?
There is some calculus involved, but the basic idea is to look at how the action changes when you make a tiny, tiny transformation that respects the symmetry. Because we're dealing with a symmetry, the action shouldn't change. When we express this mathematically, we find an equation that identifies a specific quantity that has to stay constant over time. That's our conserved quantity.
It's like solving a mathematical puzzle, and the solution reveals this hidden conservation law. It's incredibly elegant. Now, can we break down some specific examples of how Noether's theorem plays out in different scenarios?
Absolutely. Let's start with time translation symmetry. It's one of the most fundamental symmetries in physics, and it's directly tied to the conservation of energy.
I'm all ears. Lay it on me.
Imagine a pendulum swinging back and forth. Even if we fast forward our observation by an hour, the pendulum would still behave the same way. The laws of physics governing its swing haven't changed.
So time translation symmetry means the action of the pendulum stays consistent even if our time frame shifts. I'm guessing this leads to the conservation of energy.
That's exactly it. The total energy of the pendulum, its kinetic energy from the movement plus the potential energy from its height, stays constant throughout the swing.
It's like the timeless nature of physics itself gives rise to this fundamental principle of energy conservation. What about space translation symmetry? How does that play out?
If a system's action is the same regardless of its location, then Noether's theorem tells us that momentum has to be conserved. Think back to our billiard ball example.
Right, because the pool table's position doesn't affect how the ball moves. Its momentum must stay constant. Unless, of course, it bumps into something or there's friction.
Precisely. Without those external forces, the ball would just keep moving in a straight line at a constant speed. Now, how about rotational symmetry? Remember that figure skater?
Yeah, I'm starting to see the pattern here. Because a system's action doesn't change regardless of its orientation in space, that means its angular momentum must be conserved. Like the fact that the laws of physics don't care which way the figure skater is facing means their spin has to stay consistent.
You've got it. These symmetries, which might seem abstract at first, have very real and measurable consequences in the physical world. And what's truly mind-blowing is that Noether's theorem doesn't stop at these classical examples. It extends into much more complex areas of physics, like quantum mechanics.
Now we're getting to the really interesting stuff. I'm all about those quantum mysteries. How does Noether's theorem apply to the world of particles and forces at the subatomic level?
It's crucial in those areas. In quantum mechanics and particle physics, Noether's theorem is essential for understanding the behavior of those tiny particles and the forces that govern them. For example, there's this concept called gauge invariance in electromagnetism.
I have to confess, gauge invariance sounds a little intimidating. What's that all about?
It essentially means the equations that describe the electromagnetic field stay the same, even if you make certain changes to the electromagnetic potentials. It's like saying you can change your perspective, but the underlying physics remains consistent.
Okay, I think I'm following. So what conserved quantity does this symmetry point to?
Noether's theorem reveals that gauge invariance in electromagnetism leads to the conservation of electric charge.
Whoa. So one of the most fundamental conservation laws in the universe is actually a result of this underlying symmetry in the electromagnetic field. It seems like everywhere we look, Noether's theorem is connecting the dots, showing us the interconnectedness of everything.
It's a truly foundational concept. It's even central to our understanding of the standard model of particle physics, which describes all known fundamental particles and their interactions.
Okay, my brain is officially in awe. So we've talked about how mind-blowingly profound Noether's theorem is and how it touches so many areas of physics. But I have to ask, what does this all mean for us? Why should the average person care about this theorem? How does it impact our understanding of the universe and our place in it?
That's a great question. On the most basic level, Noether's theorem shows us that the universe is governed by these beautiful underlying principles of symmetry. It tells us that conserved quantities aren't just random rules, but they arise from these deep symmetries.
It's like suddenly realizing there's a pattern in something that seemed completely random before. It makes you want to search for even more patterns.
It reveals a deep connection between the elegance of mathematics and the physical world. It shows that the universe isn't just a random collection of events, but there's this intricate order and interconnectedness to everything.
It's like we're catching a glimpse of the cosmic blueprint.
Exactly. And that sense of awe is something I think everyone can appreciate. But beyond that philosophical level, Noether's theorem also has practical applications that impact our everyday lives in a very real way.
Okay, I was hoping you'd go there. Give me some examples. How does this theorem translate into something tangible?
Think about all the incredible engineering feats humans have accomplished: bridges, buildings, airplanes, spacecraft. All of these achievements rely on our understanding of conservation laws.
So Noether's theorem, through its connection to those conservation laws, has helped us create some of our most impressive technologies.
Absolutely. Without understanding those principles, designing safe and functional structures and machines would be nearly impossible. For example, engineers rely on the conservation of energy when designing a roller coaster. They have to make sure the coaster has enough kinetic energy to climb the next hill after a big drop.
That makes sense. The coaster's potential energy at the top gets converted to kinetic energy as it goes down, and then back into potential energy as it climbs again. I never thought about it that way before.
And those calculations are all based on the principle of energy conservation, which, as we've seen, is directly tied to Noether's theorem. It's really remarkable how this one idea has had such a significant impact on our world.
It makes you wonder if Noether herself realized just how far-reaching her theorem would be. What a legacy. But we've talked a lot about continuous symmetries. Are there other types of symmetries in physics?
There are. And those other types called discrete symmetries can be just as profound and perplexing.
Okay, I'm all about profound and perplexing. Tell me more about these discrete symmetries.
One example is the concept of parity, which is like mirror symmetry. It basically asks, if we flipped the spatial coordinates of a system as if it were reflected in a mirror, would the laws of physics still hold?
My gut instinct is to say yes. A mirror image shouldn't change the underlying physics.
Right. That's a very reasonable assumption, but it turns out that parity isn't always conserved in the quantum world. Back in the 1950s, physicists discovered that certain weak nuclear interactions actually violate this parity symmetry.
Wait, so a mirror image of a particle interaction could behave differently than the original interaction? That's mind-boggling.
It was a groundbreaking discovery that forced physicists to completely reevaluate some fundamental assumptions. But it also underlined how studying symmetries, even when they're broken, can reveal critical insights into the laws that govern the universe.
So it seems Noether's theorem, as groundbreaking as it is, doesn't tell us the whole story when it comes to symmetry in physics.
You're absolutely right. There are still many open questions and mysteries surrounding symmetries, especially in the world of particle physics and cosmology.
This is what I love about physics. It's like there's always another layer to uncover, another puzzle to solve. It's this never-ending journey of discovery.
Exactly. And those discoveries can have huge implications for our understanding of the universe. For instance, in cosmology, one of the biggest questions is why the universe is made up mostly of matter and not antimatter. That has to do with a very subtle breaking of a symmetry called CP symmetry.
CP symmetry, what's that all about?
It combines charge conjugation, which basically flips a particle's charge, with parity, that mirror symmetry we were talking about. For a long time, physicists thought CP symmetry was always conserved. But then in the 1960s, they discovered that certain rare particle decays actually violated CP symmetry.
So even the combined symmetry of charge and parity isn't always a sure thing. This is getting deep. What are the implications of this CP violation?
Well, it's a very active area of research, but one of the leading theories is that CP violation in the very early universe could be the reason we have a universe dominated by matter today.
That's incredible. So a subtle asymmetry in the laws of physics could be responsible for the very existence of stars, planets, and even us. Noether's theorem has taken us from rolling skateboards to the origins of the universe. That's quite a journey.
And it speaks to the power of this one elegant mathematical concept to connect seemingly unrelated areas of physics.
Before we go any further down this rabbit hole, I want to make sure we circle back to Noether herself. Who was this brilliant mind behind such a revolutionary theorem?
Emmy Noether was a truly remarkable mathematician, considered by many to be one of the most important mathematicians of the 20th century. She made groundbreaking contributions to abstract algebra and theoretical physics, all while facing significant barriers as a woman in academia at that time.
It's inspiring that she achieved so much despite the challenges she had to overcome. Can you tell us a bit more about her life and how she ended up making such a profound impact on physics?
Emmy Noether was born in Germany in 1882. Despite her obvious talent for math, she was initially denied formal enrollment at the University of Erlangen, where her father was a mathematics professor. She could only audit classes unofficially.
That's hard to believe, just because she was a woman.
Sadly, it wasn't uncommon back then. But Noether was persistent. A few years later, the university changed its policies, and she was able to earn her doctorate in mathematics in 1907.
Talk about breaking barriers. So how did she go from a math doctorate to revolutionizing physics?
Even after earning her doctorate, she faced an uphill battle to find a paid academic position. Eventually, she was invited by two renowned mathematicians, David Hilbert and Felix Klein, to work at the University of Göttingen, which was a major center for mathematical research at the time.
That sounds like a major turning point in her career.
It was. At Göttingen, Noether delved into the study of symmetry and conservation laws, and her work caught the attention of physicists, even Albert Einstein. He recognized her brilliance.
Wow, if you've got Einstein on your side, you know you're onto something big.
He even wrote a letter to the editor of the New York Times after her death in 1935, calling her the most significant creative mathematical genius thus far produced since the higher education of women began.
High praise indeed.
Yeah.
It really underscores how Noether's insights have shaped our understanding of the universe. So we've talked about how symmetries in physics are connected to conserved quantities and how even broken symmetries like those in particle physics can lead to incredible discoveries. But let's zoom out for a moment. What are some of the big picture takeaways? What does it all mean?
Noether's theorem goes beyond abstract mathematical beauty. It demonstrates that the universe operates according to these deep, fundamental principles, and these principles have real consequences. Our understanding of energy conservation, which has driven so many technological advancements, stems directly from her work.
It's like those dominoes that line up perfectly, one knocking into the next. Noether's theorem sets that chain reaction in motion.
And it makes you wonder what other dominoes are out there waiting to be discovered, what other connections we haven't even begun to imagine.
That's the exciting part. There's always more to learn. Maybe someday someone will build on Noether's work and uncover even deeper truths about the universe.
I have no doubt that Noether's legacy will continue to inspire future generations of scientists and mathematicians to push the boundaries of human knowledge.
This has been an incredible exploration. We've learned how this seemingly simple concept of symmetry has such profound consequences. We've uncovered the hidden order underlying the apparent chaos of the universe.
And we've celebrated the genius of a groundbreaking mathematician who changed the course of scientific history.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.